All right, so now let's talk about estimating probabilities and rates. Just to set it up, we're already familiar with this example of vaccination and no vaccination. And there, a key parameter, or a set of key parameters in this model are probabilities of certain outcomes. So that's what we're going to talk about. Many of you may know this already, but there's a difference between a rate and a probability. So the rate is the number of occurrences of an event in a given population over a period of time until event or end of period. You can think of it as velocity or incidence. On the other hand, or in contrast, probability is a likelihood that an event will occur in a given time interval. Thanks to the law of large numbers, over a large number of trials, the proportion of times an event will occur should be the probability. Maybe in a more tangible way. Let's say we have these, we have 9 these two are exact same copies. So we have the P1 to P9 represents 9 people. It's person 1, person 2, and so on. And then we have 3 time periods, year 1, year 2, year 3. And for each individual, we mark when an event, for example, when they got a disease, when it happened. So person 1 didn't get this disease in the 3-year window. Person 2 got it in year 2, and so on and so on. To get the probability, to get the rate, as I mentioned here, the rate is the number of occurrences until event or end of period. So to get the rate, we would get rid of all these periods. Essentially, like for person 2, they got the disease in year 2. So that's when we stop following person number 2. Person number 4 got the disease in year 3, so we stop following them in year 3, but we would do this anyway, because that's when the essentially end of the study. Person 7 gets the disease in year 1, so we stop observing them. We don't observe them anymore in year 2 or 3. So, long story short, to get the rate, we have 4 occurrences in here. And we have, so 9 times 3 is 27, minus 4 periods that we excluded. So to get the rate, we would divide 4 by 23, and this would be the rate of this disease. While probability is actually 4 divided by, in a 3-year probability, in this 3-year window, we would just divide 4 divided by 9 because we have 9 people. To get a probability for 1 year, we would have to do it.
For year 1,
Exactly.
But the chances that a person will get is more than once, isn't it? We stop following the person. For example, in this case, P7 got it in the first year, stopped following the person. Whereas, as per the definition, it is the number of occurrences of an event over a period of time. So, for a total duration of studies for 3 years, do we not want to see the number of days at the end of the study?
Yeah, it's until event or end of the period. So for this person, we had the event right here. That's
you could have got it in the second year also.
yes, yes. With this example, I want to illustrate that when you're building the model, you want to use probabilities, not rates. However, in the literature, people often present rates. So to get the probabilities, you need to do some operation to get the probability of the outcome of interest. What I also would like to stress out is that, especially in the medical literature, where they didn't have a biostatistician on the team, they often use the terms interchangeably. So when you get data, when you get parameters from the published literature, it's not always clear what exactly they measured and how. So just be careful about that. Well, to switch between rates and probabilities, there is a formula. So this will be pretty dry, but if an event E occurs with a specified population at a constant rate R, then the probability of the event E over a specified time period T is given by the equation P equals 1 minus E, which is just like exponentiated negative rate times the number of periods. So remember that in here we calculated the rate per person year. It would be, if we wanted this per 3 years, we could just multiply this number by 3, that's the RT. So R is the rate per some unit of time. And if we want the probability over a certain time period, then we just need to scale the rate to that appropriate time period. This is the formula how to get it the opposite way. It's just an inverse of the same function. Again, I know that there are some biostatisticians here, so you know this very well. But for those of you who are not that familiar with this concept, if you want to learn more, what you want to look for is Poisson process and the exponential distribution. The exponential distribution gives us, it's a distribution of time between events, and then the Poisson process gives us the number of occurrences given the rate and given the time between events. So that gives us the estimates of the probability. Essentially, these numbers are obtained from these distributions.
What is the small e?
Sorry?
That equation. What is the small e?
That's a function. Well, E is essentially a constant. It's like 2.81, something like that. But it's a standard function implemented in all software. Even like calculators have it. Yeah.
So we just plug it in and it works.
Yeah.
If there's a recurring event, suppose it's attached to categorical assume like a dead. What if it's like a flu every year? So how do you tell a different flu? Would you count?
I don't think that there is a different thing.
Yeah, if you went market here, so probability the flu came to year 3. So one event has occurred and it's event.
Yeah, I think what you're getting to is if you are, so let's say this person 7 got the flu in year 1 and also in year 2 and also in year 3. Is the probability that this person got the flu in the first year the same as the probability of the person getting it in the second year, given that he or she already got it in the first year, right? And these nuances are complicated. As with everything, like it depends. Like if you can clearly describe this conditional probability on previous experiences, and essentially the process will have on this person 7 level, you will have probably some autocorrelation. Right? Maybe this person is prone to getting the flu and therefore got it in all 3 years. That's something that ideally we would account for. In reality, it's really difficult to get such nuanced data. So this is one of the many assumptions people usually make, is that they assume that the events are independent, and then you just multiply the probabilities. It introduces some error. I admit that. But accounting for it, doing it the right way, may be just so complicated that you would never reach the result. There are trade-offs.
Can we use 2 different probabilities? What's the probability to get first? What's the probability?
Oh, absolutely. If you have the data and you know, like this is something that relates to what we already talked about. By doing this, the model would be more precise, but also more complex. What's the trade-off? I don't know. Maybe if you actually have these 2 estimates and you look at the numbers, if they're widely different, then you probably should use that. If if the difference is like 0.00001, will it make a difference? Maybe not. Yeah. Yes, absolutely. So then it depends on the condition you're studying. I hope I'm making it clear somehow.
So in this case, when you are calculating rates, you are assuming that the patient encounters this event at second year. It's not plausible or possible that he will have it in the 3rd year, and that's why you discount these 4 spires out of the patient, right? That's what you're saying.
Yes. Right?
So what if there is a possibility, let's say with the flu, that he can have it every year? He may not have it, that's a different matter. He still, only 4 patients have the flu on those 4 patients. So in that case, you do not minus those 4 spires and you do the entire period to calculate the rate?
By the definition of rate, you still do exclude that. Yeah. There is, if you added a 4th year, maybe you would get a whole different situation. But you don't have the data. So to get the estimate of the rate, we just follow people until either the event or end of follow-up.
So in case of death, that's,
Yeah. Indeed.
I think the study which is doing this should address this question. That study is going to give us the rate, and that study should address this question and give us the answer. And then we will use it for our.
Yeah. Now you actually brought a good point. So if it's an outcome that occurs every year, like the flu, maybe you don't need 3-year follow-up. Maybe 1 year will just be just fine. However, if it's death, then that's a different story. All right. So that was a very quick description of the difference between rates and probabilities. Let's talk about sources of data for probabilities. There will be slightly different sources for utilities and costs. So if we talk about probabilities, the ideal source of data would be a randomized control trial. However, as you probably know, randomized control trials have limitations. They have very good internal validity, but external validity is not as great. On the other hand, they really get you the causal effect of one intervention over the other, which you don't get from observational data. So as with everything, there are trade-offs. What do you value more? And if in reality, what will probably happen is that you will very likely have either some data from an RCT and you will have no observational data. More likely you will have observational data and no RCT. And even most likely you will have no data whatsoever. So what you can do if you have no data whatsoever, you can estimate rates using some administrative databases, perhaps. In the worst case scenario, an expert opinion can be handy. However, an expert opinion, what does it really mean, right? How certain can you be that this number that this so-called expert gave you is right? If that is the case, you really have to be careful with the sensitivity analysis. And if this expert tells you that the probability of getting the flu is 25%, maybe you would vary that parameter not from 24 to 26, but maybe from 0 to 50, just to make sure, just to cover all the possible outcomes or possible values of the actual parameter that you're using in your model. In the rare instances, if you have good estimates for whatever probability or rate from an RCT and even from observational studies, if they're exactly the same, then great, but they likely will not be the same. In that case, use both. You can run the model. Once you set the model up, changing the values of the parameters is pretty easy. So you can run the model with the estimate obtained from the RCT, which gives you a better estimate of the causal relationship of, as I said, like very good internal validity, but maybe in real world it doesn't hold. So then using the estimates from observational data may give you a better idea what's happening in the real world. On the other hand, those can be confounded.
My doubt is that in randomized control trial, as you said, the eligibility criteria are very strict. So
Yeah.
the other thing is that real life doctors produce patients and so on. So real life or real world data, you think would be more pertinent to the hierarchy of
my personal opinion is yes. I wrote this slide based on expert recommendation, and it's based on what's written in the books. It's still in the medical literature. RCTs are the gold standard. They have huge advantages, but also huge disadvantages. How you value one over the other, I think this will be probably the underlying theme of this workshop, is that nothing is certain, no one knows anything, and things are complicated. So if you don't remember anything, remember this. I will not give you a clear answer to this. I personally value, if well-executed observational studies, in my opinion, are very valuable, especially for these purposes. Some people may disagree. So if you have both sources of data, use both. You will satisfy both camps. And if the conclusions of your analysis hold, then you can say, it doesn't matter whether this person is right or this one. The conclusion of the model are the same. If they're not, then things are complicated and no one knows. Yeah, so we pretty much already talked about this. In RCTs, the main advantages is that they limit bias from confounding, they have great internal validity. Disadvantages is their selection. As I mentioned, a lot of trials are run on healthy, very often males, very often young, very often people who have the time to do this, the RCT, unless it's a condition they're already suffering from. They have limited time horizon. Doing these studies is costly, and the generalizability is not great. Yet we still do that. Observational studies, on the other hand, they can follow patients either retrospectively or prospectively. The advantages are better description of real-world situation. You can follow patients for long periods of time, especially when doing a retrospective analysis. I mean, you can still follow people for a really long time in a prospective study as well, but then you have to wait a really long time to get the result, which may be a problem, right? And you can have a broader patient population. Obviously, the disadvantages, it's pretty much mirrored. Confounding is a huge problem in observational studies because we just cannot control for everything, especially for things that we cannot observe or measure. Ideally, if you're looking for parameters, if there is a systematic review, that is a much better source of data than a single study. The main disadvantage is that there are not systematic reviews for everything. Sometimes there are not the studies for everything. What you can notice in the literature, people who do cost-effectiveness analyses, they very often publish systematic reviews as well, because in order to get the model parameters, if there is no systematic review, they have to do it themselves. And if they do it, well, here's another paper. So that's it means more work, but also you're getting something out of it. I don't know if you're aware of the PRISMA guidelines. If not, if you were to do a systematic review, look it up. Just Google PRISMA guidelines for systematic review. It tells you exactly, like it's a good cookbook of what to do, what not to do, what to report, and how to report the findings. And even a higher in the hierarchy, probably the best source is a meta-analysis, which is an analysis built on a systematic review that pulls all the data together into essentially one huge cohort and re-estimates the parameters. As with everything, there are problems because meta-analyses sometimes pool data from totally different studies that were set up in different ways, studies that use different methodologies, different populations, and they still pull everyone together, and that introduces bias as well. So again, things are complicated, but a good meta-analysis would be ideal, if there is one, as a source of data for probabilities or rates for cost-effectiveness analysis models. Well, so if studies, systematic reviews, or meta-analysis are not available, administrative databases are usually a good enough source of data. I don't really know how it works here in India, but I believe that when doctors work at hospitals, they want to get paid. So they submit bills to someone, whoever pays them. Those types of databases usually usually include good data about diagnoses, what's going on in the population. Of course, there are problems. There are patients who never see doctors. Doctors sometimes may bill a different code, either by accident or on purpose, but it happens. Let's face that. So these type of databases are not a perfect source of data for our purposes, but if there's nothing else, but there is an administrative database, it's a good place to start. I probably should mention primary data collection is always an option, but again, it's costly, it takes time. It may be difficult for a single analyst to do that. And finally, the expert judgment. Right, so the main challenges in getting probabilities is finding estimates for the right population. You can think of, so in our example, we were interested in vaccination against the flu in the elderly population. Maybe in the literature they would study the effectiveness of flu vaccine in the general population, or maybe in a population in one state, but you're interested in this analysis for a totally different state on the opposite side of the country. Would the rates be translatable? Maybe not. So it's really key when you find a parameter. At first, you will be very excited that you found, a number that you can plug in your model. But whether that number is right, whether it's relevant, that depends. So make sure that it's for the right population that you're also studying. As I mentioned before, a huge simplification of cost-effectiveness analysis is that we usually assume the probabilities to be independent, at least conditionally independent. And that's very often not the case. And the parameters that we find in the literature, we plug them in and still consider that to be independent. If you can account for this correlation within data, great. But it's usually technically difficult to do that. Next problem is that if you find an estimate in the literature, they may have made a mistake. You don't know that. So that's certainly a concern, and very often the data are not available. All right, how are we doing time-wise? Good. We end at 1? 1:15. All right, good. This is actually taking longer than I expected. All right, so let's talk about transforming probabilities. What I mean by that is the analysis usually uses some time frame. In the decision tree analysis, that's just one time frame for the whole analysis. In the state transition model, you can decide how often can people transition from one health state to another. But in any case, there's always some time frame. And within that time frame, you want to find, the probability of death, probability of getting the flu, probability of getting a side effect. When you look up these parameters in the literature, you may find a good enough estimate, but for a wrong time frame. So you will need to transform that, right, to the time frame that's appropriate for your study. So in this example, let's say we found out that the probability of death in a year is 12%. What is the probability of death in a month? Is it 1%? Yes, no? Approximately yes, but not quite. So the idea is, so how I would go about this, it's easier to flip it, right? If someone dies within a year, if there is a given probability of death in a year, 12%, that means that there's the complement, the opposite 88% of not dying within a year. So 88% will not die in a year, right? Which means, well, maybe I should have, sorry. So probability of death within a year is 12%. It means that the person can die, in January, February, March, and so on. Like in any of these months, they can potentially die. And finding all the probabilities of, let's say, if someone died in June, so you would have to find the probability of surviving up to the end of May and then dying in June. That's complicated. So it's much easier if you flip it, right? So you would get the probability of survival is 88%, which is the same as surviving every single month in the year. If the person didn't survive any of those months, they didn't survive the full year. So in this case, so we know that 88% is the probability of survival in a year, and then we can, that's the same thing as probability of survival every single month. So it's some probability of survival of a month to the power of 12. And it should equal to 0.88. So when we solve this, we find that this is the probability of survival of a month. And then we flip it back as 1 minus probability of survival of the month would be the probability of death in a given month. So it's 1.06, sorry. So quite, almost close to 1%, but not quite. But these nuances, then they can make a difference. So be careful about that. The bottom line here is never divide a probability to adjust it for the right time frame. You can either do some sort of a process as I did here, or we already talked about how to transform probability to a rate and back. And the good thing about rates is that they can be, like if you divide or multiply a rate by, you can adjust a rate for the appropriate time frame by simple multiplication or division. So an alternative approach would be, so we had the probability of death in a year. We could transform it to a rate using the formula that we talked about before. We would find that the rate of death is 0.12 and some numbers per year. We can adjust this rate, death rate, to a month time frame by just dividing it by 12. So we would get this number, and then we would retransform it back to the monthly probability, and we would get the same number. So the bottom line here is don't divide probabilities, but you can divide rates. I slightly changed the order of the slide, so this may come out of nowhere. But we will soon talk about time preference and adjusting both costs and health effects to present value. Because sometimes things that happen in the future, if you incur costs in the future, that cost has a different value today than a cost that happens, tomorrow. And We do this by something that's called discount rate, which is a fancy word for just interest rate. It's called a rate, but it's not exactly the rate I've been talking about until now. So for example, if we know that the annual discount rate is 3%, a half-year discount rate would be, so how would we get that, right? So essentially we know that whatever value we have here, to get it to present value, we need to divide it by essentially 1.03 in this case, 1 plus the discount rate. In other words, so let's say you invest 1,000 rupees here. A year from now, if the interest rate is 3%, you would expect to have 1,000 and 3% times 1,000, right? So this is just the inverse process, getting things to the present value. A half-year discount rate would do this in increments. So one way to do this would be just like, we know that the annual discount rate is the same as the half-a-year discount rate to the power of 2. Then we do the math. I will really not go over that in too much detail. The main point of this is that the discount rate is a very specific kind of rate, and the standard, essentially, these formulas don't apply here. It's just terminology that's not very consistent. Right, so I think I reached the end of this slide deck, and even though I still have 10 minutes, I don't think it's a good idea to start a new one before lunch. So exactly. So if there are questions, please ask them.
Concept of discounting.
Yeah. I'm sorry. I should have talked about discounting first, and I will. I don't think I'm talking about it.
The formula. We understand the concept, but the formula.
Yeah. I will talk about it later. Like I had this course developed a few years back, but now to make sure that it fits the structure of this course, including the practical examples, I switched certain things back and forth, and now I see that this was not ideal. Maybe I'll get back to it when we actually talk about discounting.
So why do we say that rates can be divided? Because the event can occur at any time. So how can we divide the unpredictable?
Yeah.
How about the
Well, both rates and probabilities are attributes of a population. Like they're both uncertain. Like rate will tell you nothing about what will happen to one particular individual. It's just you take data from a population, you look, how often certain things occur, and by the definition of rate and essentially by the mechanics of it, like the idea is, so let's say if you follow enough people to observe a good estimate of a rate in 1 year, if the rate is constant in the second year, you will see just twice as many events. That's the idea behind it. So then to get the 2-year rate back to the 1 year, you just divide it by 2.
real life is maybe earlier or something?
Yes, there will always be imprecision. Like the main assumption is that you need a large sample large enough to get a good estimate of the rate. And of course, like the underlying assumption is that you assume the rate to remain constant. Rates can change over time, especially when there are interventions. That's the whole point of them, right? To change the rate of certain occurrences. So in a way, yes, like there are many things that can influence a rate. But with the assumption is that if the rate really, if the underlying data generating process remains untouched, stable over time, then if you have 2 periods, you will see twice as many events